to is on two means, specifically independent samples. And when it comes to independent samples, these are where the sample values from one population are not related to or somehow naturally paired with or matched with the sample values from the other population. So if the samples have different sample sizes with no missing data, they kind of have to be independent, right? Because they're definitely not paired. An example of an independent sample is the heights of men and women, since men and women are not necessarily dependent on each other. They could just be a random sample from each. A dependent sample, however, or a matched pairs sample, is a sample where the values are somehow matched based on some inherent relationship or characteristic. An example of that is, for example, a before or after test, quiz, that type of thing. Heights of husband and wife, height of father and son, mother and daughter, that type of thing. If two samples have the same sample size, those samples may or may not be independent. It depends on the situation. So that doesn't have as nice of a inference there. But the specific inferences about two means independent samples with unknown and presumably unequal variances. And this slide just has the requirements for the test. The variance, the standard deviation of the first sample and standard deviation of the second are unknown, and we do not assume that they equal. So we just plain don't know. The two samples are independent. Both samples are simple random samples, and either or both of this last one has to be satisfied where the sample sizes are large. So the first and second sample, both of those sizes has to be greater than 30, or both populations have normal distributions. And just as we saw before when it comes to the t-test used for the inference of either one or two means, this is robust against departures of normality. So it works with small samples with no outliers, but yet has no extreme departure from normality. So we could still use the test regardless of the 30 there being not exactly met as much, but we specifically need it to have no outliers and not be extremely far from the normality aspect of that. And when it comes to this test, we need to use the hypothesis test statistic for two means independent samples where the null hypothesis is that the two means are equal. So the mean of the first population equals the mean of the second population. We could also write it as the mean of the first population minus the mean of the second population is equal to 0. Both mean the same thing. The t-score is equal to x sub 1 bar minus x sub 2 bar. So the first population, well, the first sample mean minus the second sample mean minus the difference in the two population means. Again, this should be 0. It usually is. Divided by the square root of the sample variance for the first sample divided by the sample size of the first sample plus the variance of the second sample divided by the second sample size, with a degree of freedom of whichever of these two is smaller, n sub the first sample size minus 1 or the second sample size minus 1, whichever of those two is smaller. Technology, though, when we use it, such as SAS, which we'll do in a moment here, this uses a more complex formula for the degree of freedom, and I definitely do not recommend doing this out by hand. But the actual formula that SAS uses, at least, takes this a plus b squared divided by a squared divided by n sub 1 minus 1 plus b squared divided by n sub 2 minus 1, where a is the variance of the first population divided by size of the first sample divided by the sample size of the first sample, and B is the variance of the second sample divided by the second sample's size. The p-value critical value can be computed in SAS, and we have the confidence interval where we just take the sample mean for the first sample minus the sample mean of the second sample, plus and minus that margin of error, which is the t-square alpha divided by 2 times the square root of x sub 1 squared divided by n sub 1 plus x sub 2 squared divided by n sub 2, with degree of freedom being the smaller of n sub 1 minus 1 and n sub 2 minus 1. And actually this is supposed to be an x here, not an s. Let me just quickly change that. There we go. And again, technology uses that more complex looking formula that looks like a behemoth, to put that mildly. But for an example of using this formula, let's take example 1 here. Data set 14 passive and active smoke indicates measures of cotinine in nanograms per milliliter in subjects from different groups. Cotinine is produced when nicotine is absorbed by the body, so cotinine is a good indicator of nicotine. Listed below are the summary statistics for a group of smokers and another group of subjects who do not smoke but are exposed to additional tobacco smoke at home or at work. Use a 5% level of significance to test the claim that the population of smokers has a higher mean cotinine level than the non-smokers exposed to smoke. And then, do smokers appear to have higher levels of cotinine than non-smokers who are exposed to smoke? For the smokers, we have a sample size of 40, X bar of 172.5 nanograms per milliliter, sample standard deviation of 119.5 nanograms per milliliter. And for the non-smokers exposed to smoke, sample size is 40, X bar is 60.6 nanograms per milliliter, and sample standard deviation is 138.1 nanograms per milliliter. So for this, we don't know anything about the population standard deviations. So the first population standard deviation and the second population standard deviation are not equal, and they're unknown in this, which is exactly what we want for this test. Both of these are independent, right? Because whether you smoke or not, it does not have an impact if someone else smokes or not, unless they know you, but that's not indicated in this. We have a simple random sample for this. So let's see. Simple random sample. And we could see, since both of these have a sample size of 40, the first and second sample sizes are both equal to 40, so this passes the approximately normal requirement. So it's approximately normal. And that L did not show up on there. There. Approximately normal. We could write out the hypothesis test as the null hypothesis where the two means are equal, and the alternative being that the smokers group, so this is going to be the first mean is greater than the second mean, where the first mean is average cotinine for smokers. And this is the specific level I should also mention. So average cotinine level for smokers is the first mean, and the second one is for the non-smokers. But in order to do this, we could toss this here into SAS over here on the right. But before doing so, I should probably note, when it comes to this sample statistics down here, and I didn't really do much with it just yet, these two, it's typically helpful to have it written already out in a data table all nicely. So for example, the one I'm using here, I put it into a table here where I have certain values on here. Now, the reason for this is so SAS can read it correctly, since we're given summary statistics right here. So you would first have one column that lists the two populations, so smoker versus non-smoker. I use just very brief descriptors for each one, just because, well, number one, we already have what they all mean. But number two, I did that to make it a little bit easier to actually type out what each of these are. This middle column that has underscore stat underscore, it needs to have all three of these in there. So N for the sample size, mean for X bar, and STD for the sample standard deviation. And then I put the actual values from here instead of this last column. And I gave it a name, although I know that 40 does not refer to a cotinine level, and neither does this 40. But I called it cotinine since most of the data in this particular column does match with the cotinine levels. So I'm going to be using this particular data set. And I need to open that in SAS, as a matter of fact, which I just realized I did not do before making this video. So let me very quickly import the smokers Excel document on here so we could actually use it. Okay, now that that's in there, what we need to do in order to conduct this particular hypothesis test, instead of SAS, and I should have clicked on instead of here so I can actually type, there we go, we need to put in the following. We're using a procedure here, so proc Ttest, since this is a Ttest as we've seen. The data that we're going to be using, I call this work.smokers. And we were given a specific order in it. It typically, I believe, defaults to using the order in the data. But I'm going to put order equals to data just to make sure it doesn't mess anything up on us. We were given an alpha of 0.05 instead of the actual problem on here. And from this, we want to test the difference between these two. Do note that our options for test are either difference or ratio, but we are not using ratio in these. It's always difference. So test is equal to difference. The sides that we want, this could either be L for lower, U for greater than, or 2 for not equal to. In this case, we have a greater than symbol, so this is going to be a U. We could also specify the value of the null hypothesis, so H0, and we could set that equal to a value. It defaults at 0, so you technically don't have to put it in there, but I'm going to include that in here just for the purpose of just showing you it, and then a semicolon. Here for the class variable, we need a class. The class we are going to use, and I probably should have left this up, but I did not. The class we are going to use is this first column, which we called smoker. So, the first column we called smoker. The variable that we are going to use is this last column, which is the reason why we kind of needed to give it a name. I called it cotinine. So this last column we're going to call cotinine, and that goes for variable. And then we finally end it with run. And then we run the program, and once it goes, which I already finished before I could even finish talking, but as you could see, it gives us our t-test for this. And we specifically were running the hypothesis test. So the only thing that we particularly care about here, since we are assuming these are not equal to each other, we only need this last row right here. So it's called Satterthwaite, where the variances are unequal. We have a degree of freedom of 76.423, right? And we use a t-value here, which was 3.88. So if we actually calculate this out by hand using that incredibly long and difficult looking formula, we should get about 3.88. And hint, since yes, I did it out, it does make that. The p-value for this is going to be very small, 0.0001. And if you need a very quick visualization of this, and something that hopefully doesn't look to be too terrible, 3.88 would be what? Here-ish. And we want the area above that, which, as we could tell from my very bad drawing, can't be too big. And based upon the probability that we got, it is not too big. 3.88, p-value 0.0001. And yes, so from this we can write our conclusion. I should probably note something. There is a slight issue with this, specifically with the confidence interval, but we'll get to that in the next example. So I'll save that for the time being. You can probably guess it by just looking at this, what's wrong. But we need to write out our conclusion from this. So we can go in here, extend this down a little bit to make sure I have enough room. Okay, so the conclusion that we can write about this is at the 5% level of significance. And as you can tell, our p-value of 0.0001 is indeed a lot less than 5%, so we are indeed able to reject the null hypothesis. So the conclusion then is there is sufficient evidence to support the claim that and if I could type, that would be helpful, that the population of smokers has a higher mean cotinine level than the non-smokers. Exposed to smoke, which we could tell just based upon that p-value that we got. Again, all fine and dandy for that. Furthermore, it appears that smoking is associated with higher levels of cotinine. Than non-smokers exposed to smoke. Again, due to the fact that we got a p-value so low, and the fact that the cotinine mean level for smokers is indeed a lot higher. But that's just based upon this hypothesis test. For my second example here, I have using the same data that we just had. We want to construct a 90% confidence interval estimate of the difference between the mean cotinine level of smokers and the mean cotinine level of non-smokers exposed to smoke. For this, since we are using a 90% confidence interval, and I know we specified alpha to be 5% here, but in the same part on here, where under the Satterthwaite here, we have a confidence level for the mean. There is indeed a slight issue here, though. Right? The lower bound of this is 63.8. That's fine. It gives a upper bound of infinity. Unfortunately, infinity is not the upper bound of this, which is the reason why it's unfortunate that it gives that value, because that's not really the answer that we're actually looking for. The lower bound, though, is indeed 63.8, so we could include that on here. 63.8, and the units of measurement were nanograms per milliliter. This would be less than the actual population mean minus the second population mean. And, you know, the upper bound of this interval is indeed high, but it's not infinity. So to actually calculate that, we unfortunately need to do a little bit of math here out in order for us to actually come to the value of it for this. Alright. So because we have a sample size of 40, the degree of freedom we're going to be using is 1 minus 40, so 39. And both of which are 39, so we can't really dictate anything with that. And for us to do this, we need the critical value. Since we have a 90% confidence interval, that means alpha is 10%, which means this critical value is for t sub 0.05. And we've calculated that before. If you were to look this up, this would give us a value of 1.685. Positive and negative because this is a confidence interval. The margin of error that we need for this is this incredibly complex looking formula. E is equal to this 1.685 times the square root of the first standard deviation, which was 119.5. I'm going to square that and divide it by the sample size of 40, plus the second standard deviation of 138.1. I want to square that and divide by 40 again. Tossing this into a calculator will give us an answer of about 48.65276 nanograms per milliliter, but I ran out of room to write that. And to get the upper bound of this, the first sample mean was that 72.5, second was 60.6. And the difference between those two, if we were to toss that into a calculator, would be this 111.9. So x1 bar minus x2 bar is equal to 111.9. So in order to find this particular value, we need to add these two numbers. And I might as well write that down here. 111.9 plus 48.65526. If you toss that into a calculator, you'll get an answer of about 160.0. About. And again, this is nanograms per milliliter. Alright. And we can write out our answer to this as we are 90% confident that the limits of 63.2 nanograms per milliliter and 160. Oh, wait, this is 63.8. I put 0.2. 63.8 nanograms per milliliter and 160.0 nanograms per milliliter actually do contain the difference between the two population means. And then we could say the limits do not contain 0, which we could tell since 63.8 and 160, that's nowhere near 0. So it does not contain 0, which suggests that the mean cotinine level of smokers is greater than the mean cotinine level of non-smokers exposed to smoke. An alternative method that we could use, assuming that the two standard deviations are equal. This, though, is highly unlikely. But if the two standard deviations are not known, but we could assume that they have the same value, the sample variances can be pooled to obtain an estimate of the common population variance. So, pooled estimate of the variance is of the population variance is a weighted average of the same variances. And as you could assume, it is a very complex looking formula which did not automatically put itself up there, so let me toss that in. There we go. So the actual formula is this one here that I just copied. We take the square the variance, the pooled variance, as n sub 1 minus 1 times the first sample variance plus n sub 2 minus 1 times the second sample variance divided by n sub 1 minus 1 plus n sub 2 minus 1. And the t-squared that we have is the same basic one. x1 bar, x sub 1 bar minus x sub 2 bar minus the two population means subtracted by each other divided by the square root of the pooled variance, pooled sample variance divided by the first sample size plus the pooled variance divided by the second sample size. And the degree of freedom is n sub 1 plus n sub 2 minus 2. And again, we have our confidence interval, the same basic thing, with the margin of error being t sub alpha divided by 2 times the square root of the pooled variance divided by n sub 1 plus the pooled variance divided by n sub 2. And the degree of freedom is n sub 1 plus n sub 2 minus 2. And we should know when to assume the two standard deviations are equal, and that is if randomness is used to assign subjects to treatment and placebo groups, we know that the samples are drawn from the same population. And if we conduct a hypothesis test assuming that the two population means are equal, it is not unreasonable to assume that the samples are from populations with the same standard deviation, because again, they're drawn from the same sample. But we could still check that, and there are ways to check it, but not necessarily what we're doing right now. The pooled sample variances, they cause the degree of freedom to be a little higher when we pool them. So the hypothesis tests have more power, and the confidence intervals are a little narrower. And in the homogeneity of variance in the two sample means test, this was an article published by these two authors, Mosner and Stevens, in the American Statistician Journal, Volume 46, Number 1. The authors note that the assumption is indeed rare to have when these two are equal, and it's greatly suggested to use it the test when it's not equal to, due to the fact that we usually don't have the ability to say that these are equal. An alternative method for when the two standard deviations are known, again it's very rare, but if they are known we can use the normal distribution. And the new requirement is that the standard deviation of the first population and the standard deviation of the second population are known. Then we have a test statistic z, which follows a normal distribution. X sub 1 bar minus x sub 2 bar minus the population mean of the first population minus the population mean of the second population divided by the square root of the population variance of the first population divided by the sample size of the first sample plus the population standard deviation of the second population divided by the sample size of the second sample. And again we have the confidence interval, the same thing, but margin of error now is z sub alpha divided by 2 times the square root of the variance of the first population divided by the sample size of the first sample plus the population variance of the second population divided by the second sample size. And then how about if one standard deviation is known and the other is unknown? Then it's basically the same procedure as what we did in the first example. So for this, if the first standard deviation is known but the second is not, we use the same procedure as both were unknown, but we place the first sample standard deviation with the population standard deviation. So use the degree of freedom of the first population variance divided by the sample size of the first sample plus the sample standard deviation of the second sample divided by the sample size of the second sample square, this whole thing squared, divided by the sample variance of the second sample divided by the sample size of the second sample squared divided by the sample size of the second sample minus 1. A lot of samples, right? And then the last thing on this, for when it comes to two independent means, we should assume that the standard deviations are unknown, that the population standard deviations are unknown. We should never assume that they are actually equal. And use the test statistic and confidence interval given when the standard deviations are not known for these. Let me know if you have any questions or concerns. Thank you.